Hello everyone! After 7 long years, Hollow Knight Silksong is finally here. Silksong clearly demonstrates the experience Team Cherry has gained when it comes to crafting intricately detailed and beautiful environments. Unfortunately, art skills can only take you so far, and sometimes we need to learn a little about how rendering works in order to solve some really ugly situations, which Silksong is unfortunately plagued with. While other YouTubers can explain to you how Silksong's world and narrative come together, today we'll be looking at the techniques Team Cherry used for the game's graphics, why it looks good, and how it could be even better. With an engine like Unity at their disposal, Team Cherry could make use of any number of shader techniques that I've covered in my videos, but obviously shader development is really hard, so instead they opted to just import scans of the artist's drawings directly into Unity and use them as is. We don't need to speculate on the techniques used because, just like our overview of Lethal Company, we can make use of a frame capturing tool to inspect each and every GPU command needed to construct a frame of Silksong. From my time examining the visuals of the game, I have identified 5 major components of Silksong's graphics you should know about if you want to create something similar. But what about the major graphics issue the game has? Sadly, Silksong is very sick and needs a cure. This screenshot should very clearly demonstrate what the problem is, but if you can't see it, this is your last chance before I ruin your perception of video games forever. The diagnosis is color banding, an issue every game has to deal with somehow, but it seems Team Cherry decided to just let it rip, which is unfortunate because this horrible color banding is right at the start of the game and really kills the vibe of what should be a very beautiful moment. To understand how to fix this problem, we first need to identify the cause, so let's get started by studying a frame to see how Silksong comes together. But first, a word from this video's sponsor. This video is sponsored by War Thunder. War Thunder is the most comprehensive vehicle combat game ever made, available for free on PC, console, and mobile platforms. Developed by Gaijin Entertainment over the past 15 years, War Thunder has grown massively since its initial 2013 release, evolving from aerial combat simulation to now including ground and naval battles as well. I remember playing the game when it first came out and being super excited for those planned updates with these other kinds of combat. The idea of mixing these battles together in the same lobby felt like the technology of the future. Gaijin Entertainment delivered on these promises, and you can now take command of over 2,500 tanks, planes, helicopters, and ships from 10 different nations, ranging from century-old biplanes to modern fighter jets and battleships. Immersive isn't just a buzzword here, as every vehicle in the game is true to life, intricately modeling each individual component that makes up the vehicle to achieve realistic vehicle damage paired with a fancy X-ray view. Join a community of over 95 million players in War Thunder today entirely for free on PC, console, and mobile platforms using the links below. New and returning players who haven't played in the last 6 months will earn a free bonus pack of goods to help get you started, but this offer is only available for a limited time, so be sure to claim the rewards while you can. Many Silksong players ask the question, does this game use background images? Here on Event 525, we see the background is drawn to the screen. If you remember from the Lethal Company video, Unity renders upside down until the last draw, so if we rewind even further, we can see that the background is not a skybox at all, but actual sprites drawn one by one. You may be wondering why it looks really ugly, and that's because our frame preview is upscaling the actual background size of 640 by 360, meaning the background is rendered at 1/16 of the actual game resolution, since this frame is 1440p. This also gives us an idea of what the background would look like without any filtering, so not great. Silksong is the first game we've looked at that draws back to front, also known as the painter's algorithm. We typically don't see this anymore in modern games. With the rise of more complex shader techniques, each individual pixel is becoming more expensive. Any pixel that is overwritten is wasted work. Silksong is a 2D game though, so it doesn't really matter all that much that there is a ton of overdraw. There's no complex shaders, so the wasted work is negligible, and it simplifies transparent geometry rendering. I mention this because some people can be overly obsessed with performance when it otherwise will never matter beyond self-satisfaction. Silksong's graphics are fundamentally inefficient, but the frames still render in less than 500 nanoseconds. GPUs are really fast. With everything in the background rendered, we progressively blur and upsample the lower resolution render to the actual target resolution of 1440p. This brings us to the first major component of Silksong's visuals, depth of field. Functionally, the background blur hides that it's rendered at a lower resolution, but aesthetically it sells the scale of the world and the distance of these objects from the camera. It also puts the focus on Hornet and other near-field objects instead of muddying up the screen with irrelevant visual knowledge. This is a huge win for depth of field fans, all one of you. With the background fully rendered, it's time for the main event, rendering everything else, which raises an important question. Is Silksong 2D or 3D? Much like discussing if a hot dog is a sandwich, whether or not you consider Silksong 2D or 3D is going to be based on technicalities and semantics that ultimately results in words having no meaning at all. But if you ask someone on the street what they think, the answer would most likely be 2D because that's the vibe. Unfortunately, Silksong is technically 3D. A disaster of a factoid for YouTube comment sections and Reddit threads, and this is because of the game's camera. In the real world, when you are driving along the road, the trees next to you are going to seem like they move a lot faster than the mountains far in the distance, even though you, the viewer, are moving at a pretty constant speed. The difference in the perceived position of an object in space from 2 points of observation is known as parallax, a word so fun you have to say it twice. Consider 2 moments of our peaceful summer road trip wistfully gazing at the distant mountains through your passenger side window. The nearby trees are exhibiting a large parallax because they appear to have moved much farther than the mountains in the distance, meaning the mountains exhibit very little parallax. The car about to collide head-on with us does not exhibit any parallax because our 2 points of observation are the same, but we can tell it's getting closer due to foreshortening, where nearby objects appear larger than distant objects. These 2 principles of observation allow astronomers to predict the distance of stars from Earth and also are 2 things we can simulate in video games to add perceptual depth. Any means of adjusting the parallax of game objects is known as parallax mapping. The simplest method is with the almighty perspective projection matrix, which we learned about in my PS1 video, where I explained how the PS1 could render 3D worlds despite only having 2D graphics hardware. Returning to Silksong, the game uses a perspective camera to achieve the parallax effect by actually positioning the sprites in 3D space to get desired results. You can see that the background moves much slower than the near-field objects. How cool. Technically speaking, any game that adds perceptual depth at all is 3D, while older games like the original Metroid or Kirby are true 2D, as if there's any background at all, it moves the same as everything else. There is, of course, 2.5D, but the definition of that is up in the air. Technically, it is a 2D game with sprites that appear to be 3D objects, games like Age of Empires, and many other old PC games, which Silksong does not have, so it is not 2.5D. It doesn't really feel right to refer to Silksong as a 3D game. All gameplay takes place on a 2D plane, and if the camera were to view the game from any other angle, the world wouldn't make sense. Nowadays, parallax mapping is a very common feature of 2D side-scrollers. Team Cherry has the privilege of getting to use a perspective camera to get parallax for free because the game art is painterly and anti-aliased, so it's just the easiest way to get the desired effect. Other 2D games don't have this luxury. If your game is pixel art, then you need pixel-perfect parallax, otherwise you will run into sub-pixel rendering problems, and so those games need a more sophisticated parallax solution. But are you really going to look me in the face and tell me Kirby Squeak Squad is a 3D game? The second pillar of Silksong's graphics after depth of field is parallax mapping, probably the most important thing on this list. Moving on, now it's your turn. I'm tired. I'm going to play a short clip, and I want you to tell me what you think is the next important piece of the visuals. Did you see it? On the left side of the screen, barely visible on camera, a white, translucent presence slowly creeps into frame. Wait a second. That's not a ghost orb. Aww. That's a particle. Team Cherry uses particle systems to add more depth, movement, and visual variety to an otherwise motionless, dying world. Silksong is juiced to the gills with particles, from dust to pollen to grass to whatever else. You can really tell that they had fun adding them in wherever they could. No spoilers, but my favorite particle effect is when one boss does an attack from above, and when they hit the ground, a bunch of particles fly up. It's really pretty. Just imagine it in your head or play the game, I guess. Particle systems sure sound sophisticated, but is Team Cherry actually doing anything complicated for these beautiful effects? Not really. Each one uses the same little texture, and I assume they're using Unity's built-in particle tools for simple animation and spawning, however that works. In the frame debugger, it's all just unlabeled byte data, so they could really be doing anything in there. This third major component of Silksong's visuals is something pretty much every game dev should learn from. All the engines have their own simple particle tools that you can use and abuse to make your games look more interesting. Team Cherry demonstrates that the only thing you really need is a tiny texture. This applies to both 2D and 3D games, but in the former case, you can really go crazy with it since there's pretty much no performance concerns on any post-2015 hardware. As established, Silksong is inherently unoptimal. Check out this geometry. There's nothing to be afraid of. Add particles to your game. After all the objects in the scene have been drawn, it's time to finish up with post-processing. The current scene looks really nice already. It goes to show just how beautiful the game's art is without any additional effects. Unlike particles, post-processing isn't going to save a game without any sauce. Instead, it's more like a set of spices to bring out different flavors. Our first post-processing effect is a vignette, darkening the edges of the screen. How dramatic. This isn't a traditional vignette, as it is not relative to the camera view, but rather is centered around Hornet herself. You can see that when I jump up, the effect follows. So this vignette is more so to accentuate Hornet as a light source, darkening the areas on screen further away from her. The next pass makes this even more obvious, as the area around Hornet is brightened. These two effects may be simple, but when combined, adds some much needed contrast to the render, while also putting more focus on Hornet. Lastly, we draw another vignette, but this time it has a fancy fog texture. The fog fades out towards the center of the screen to prevent Hornet or anything else from being obscured. It also makes the previous vignette look more like volumetric shadowing on the fog, which is pretty cool. I said lastly because technically none of those were post-processing effects. They were just more sprites that looked like post-processing effects. Next, we have the first actual post-processing effect, everyone's favorite, bloom. You can see that the bloom accumulation buffer is very slight, but it makes a difference when blended in. Our frame capture comes to a close with the final Unity Uber post-processing pass, which Team Cherry uses to apply some final color corrections to make everything more vibrant. It's a bit of a cop-out to just say post-processing as the fourth big component of Silksong's graphics, so instead, I'll specifically point out bloom as something you should be aware of and experiment with in your own projects. Bloom is consistently hated on as an effect, but I can assure you that 99% of the time, bloom can and will make your game look better as long as you keep it tasteful like Team Cherry has. It adds a slight gradient to the harsh black outlines of the artwork. Without the bloom, the game would look flatter. But Acerola, what about the big issue you pointed out earlier? If the frame is fully rendered, then you skipped over the color banding that you made such a big deal about. Whoops, I got so distracted by how beautiful this game is that I forgot it had any issues in the first place. The last important piece of Silksong's graphics is, of course, the hand-painted art. No amount of shader effects on 3D models will be able to replicate the charm of the game's artist-authored sprites and animations. It is an insane feat that Team Cherry was able to create so many unique environment assets. Even most particles are unique to the area. This complete reliance on textures is ultimately the source of the game's graphics issues though, and it's easy to understand why. As explained in my long video about color spaces, color banding occurs when we need more colors than are available to smooth out a gradient, resulting in obvious, distinct blobs or bands of color. Many things can cause color banding. In fact, everything on this list aside from the parallax can cause color banding, now that I'm thinking about it. But the most common cause is compression, like JPEG compression. The color banding is simply the visual indicator that the underlying data isn't very accurate. Sometimes color banding is an intentional effect and can look nice, but most of the time it is not intentional and looks really ugly. This means the first question we need to ask is if our criticism of Silksong is justified. Is the color banding an intentional artistic decision, or is it an error? Considering a patch came out after the game's release, adding an option to try and reduce the color banding, I am leaning towards unintentional error. But no need to fear, there is a solution. And no, it's not the one they added, because it doesn't really do anything. Like I said earlier, almost all of these things we've talked about can cause color banding one way or another, but the most likely culprit every time is texture compression, which we can easily verify. When the fake light is drawn behind Hornet, we check the bound texture resources and find a texture atlas filled with various glow and fog effects used throughout the game. Zooming in on the glows, we can see that the color banding is part of the texture itself and not the result of any shader quirks. This means that the terrible color banding I've pointed out is actually always on screen because it's baked into the texture, which is very strange. If it's always there, why can't we really see it here, but it's so bad here? Since this is an image data issue, we can easily reproduce the problem in Photoshop, which is probably where Team Cherry authored the textures anyways. Starting with a blank neutral gray canvas, we draw a circular gradient with a similar vibe to the Silksong glow. It's pretty difficult to see the glow here, which is sort of like our Graymore frame, but if we change the background to black, it's a color banding jump scare. Unfortunately, our eyes betray us. Humans are just naturally more sensitive to slight differences in low brightness values. There's other stuff that can impact color banding, such as your display settings or in-game gamma settings, but it's mostly our biology that is to blame. Okay, smart guy, why not just use the blur tool to smooth out the gradient even more to get rid of the banding? This doesn't work. The blur tool has no impact on the gradient because, like I said, there just isn't enough available colors for our displays to close this gradient. If we had a high dynamic range display, then this would solve the issue, but most people don't have those. So how do we fix this? With an optical illusion, of course. It's already been mentioned and implemented by Team Cherry post-release. One of my favorite things, dithering. They just didn't implement it in a way that fixes the issue. Thankfully, I'm here to do that work for free. Patreon link in the description. Dithering is the intentional injection of noise into an image to spread out and blend bands of color into each other. There's no real mathematical blending, but with the right mix of the same low precision colors, we can create a perceptually smoother gradient. The noise we use has a major impact on the results. We could use white noise or blue noise or literally anything really, but the most well-known dither techniques are Bayer dithering and Floyd-Steinberg dithering. The latter isn't an option because it is generally too expensive to compute. Bayer dithering is the typical stylized dither option, but it's less effective at fixing color banding. Unfortunately, Team Cherry used Bayer dithering. Photoshop actually has a handy-dandy dither option for the gradient tool, but it kind of doesn't do anything except fix the edges a bit. Unfortunately, there isn't much we can do to fix this in Photoshop itself. As cool as dithering is, it has one major fatal flaw. You can never, ever touch it after it's been applied, unless you want to ruin everything because of how textures work. Anyone that has tried to post a dithered image on social media understands this very well. In order for it to work effectively, a dither must be pixel perfect and viewed at its exact resolution. Any filtering after the fact will probably destroy your image because dithering is not meant to be resized. The dither examples I'm showing you on screen probably look worse due to video encoding and resizing on different video player resolutions. We can see error diffusion dithering on Photoshop by changing to indexed color. This isn't to show a fix, but to demonstrate how dithering is instantly destroyed upon resizing. Just to make sure YouTube doesn't ruin the demo, please enjoy these photos of my screen. Zooming in isn't so bad, but it just gives us the same problem. The dither pattern is enlarged and is just as obvious and ugly as the original color banding, but zooming out completely destroys the texture. Only when viewed at its original resolution does the dither look proper, which ultimately defeats the purpose of a texture. Game textures excel at minification, which destroys the dither, but magnification isn't their strong suit, and it is ultimately what's causing the Silksong color banding. If we zoom out on our pre-dither gradient, the color banding becomes imperceptible. Only when zooming in does it become apparent. This becomes an even bigger issue on larger displays, such as my 4K monitor. More pixels means the texture needs to cover more space and be enlarged if it isn't a high-resolution texture, which Team Cherry's glow sprites are not. They are enlarged in-game to cover more space on the screen. The Switch version of Silksong probably doesn't have such a problem due to the lower resolution screen, but I don't have a Switch to verify. We can lower our game resolution to 1080p though, and see that the color banding is still obvious, so it's not just a 4K gamer problem. Thankfully, graphics programming is here to save the day, as we can achieve pixel-perfect dithers at runtime with one cheap line of shader code. Over here in Godot, I've made a little scene scene to demonstrate the perspective camera and resulting parallax between these scarecrows I made out of quads because I felt inspired by Silent Hill F. We have our hornet-sized quad that the camera is focused on, and after we import our glow texture we made in Photoshop, we place it behind Hornet. To ensure that the size of our glow matches the game, I took a screenshot of the glow mesh, set it as the background, then enlarged our glow until it matched. Life can be so simple sometimes. Once our background is set to black, the enemy reveals itself, and it's time to overhaul our sprite shader to cure the sickness that plagues our texture. If everything in your game is just a textured quad, the shader is nothing more than a sampling of the texture using the quad's UV coordinates, but our glow is less of a color texture and more of a transparency mask. We still sample the texture, but as data is used for the alpha value of the pixel, that way we can actually see through the glow, and now it's time to dither. First, we need to choose a noise to dither with. Team Cherry used Bayer dithering. Bayer dithering works by tiling a small two-dimensional set of values across the image, using the screen coordinates of the pixel to index the array. This is what makes the dithering pixel perfect, as it is based on the screen and not mesh data like UV coordinates, which would transform along with the mesh. Screen coordinates are always just screen coordinates. After we get the corresponding Bayer value, we convert to the -1-to-1 range, add it to our sampled alpha texture value, and we have a beautiful Bayer dithered glow. Okay, the dither is looking a little strong, so we can control that by multiplying the dither value by some small number. Remember, we're trying to add just enough noise to make the banding go away, but not so much that the noise becomes obvious and replaces the color banding as an ugly stain on the render. This is ultimately the issue with Bayer dithering. Its other name is ordered dithering, because that's how its histogram looks. Nice, orderly, and perfectly uniform. Such an obvious pattern will trigger our pattern recognition though, shattering the illusion of a smoother gradient. While Bayer dithering does look really cool, debanding is simply not the place for it, so we'll have to look elsewhere. We don't have to look very far though, as thanks to Activision graphics programmers trying to create a noise optimized for temporal anti-aliasing in 2014, we have a simple one line of code solution to our color banding problem. Interleaved gradient noise, or IGN for short, is probably the most underrated graphics invention of the past decade. It is truly the holy grail solution for many different problems for reasons that are very difficult to explain. IGN is exactly what it sounds like, a bunch of interleaved one-dimensional gradients that are pretty much uniformly distributed. The noise looks like this. Now imagine this noise is tiled across your screen behind the scenes, and you are playing Fox from the hit game Super Smash Bros. Melee for the Nintendo GameCube, practicing your wave dashes. If each wave dash travels the same distance of pixels across the screen, then the set of positions after you have finished traveling across the arena will result in a beautiful gradient hidden in the noise. This holds true for mostly every line of samples of equal distance. It's actually really cool and also beautiful if you think about it. In lamer terms, this means that anything traveling across the screen at a constant rate is going to also travel along that smooth gradient. An example from the SIGGRAPH presentation on the development process helps visualize why this is so powerful. If the noise were to represent a rotation applied to an object, the interleaved gradients will produce a generally smooth rotation as the object travels across the screen, which would not be the case for something like white noise, where the rotation would be purely random. Remember that our noise is based on screen coordinates, and many modern techniques such as ambient occlusion, shadows, and global illumination start in screen space now due to being the result of stochastic ray tracing. If you remember from my video on physically based rendering and the rendering equation, which is an integral, video games don't really have the time to spend on computing the infinite sum of reflected light from all possible incoming light directions in the hemisphere surrounding a pixel's world space position. So instead, graphics programmers make do by getting a good enough approximation from as few direction samples as possible, which is ultimately going to be determined by some random process, hence the stochastic part of stochastic rendering. Because it's a random approximation and not the full infinite sum of the hemisphere integral, the noise will reveal itself in the output, so we should be wise about the noise that drives the RNG. Some different examples from the PowerPoint show how noise will affect shadow sampling. Uniformly distributed noise causes banding, white noise looks like shit, and I'm sure if you've made the connection by now, you can probably guess how Bayer dithering would look if used here, since this is basically just our glow texture problem again, and while Bayer dithered shadows would look really cool in a stylized game, not so much in a realistic game. This is where interleaved gradient noise enters the arena. Combining the spatial coherence of uniform noise values with a slight chaotic twang of white noise, we get the best of both worlds. To calculate this noise, we use our screen space position and take the fractional component element of the dot product with these two numbers, multiply by this third number, then return its fractional component. Where these numbers came from, or how they derived them, who knows, but the results speak for themselves in the shadow samples. No banding, no chaos, but instead, a secret third thing. Since shadows are very expensive to render, the noise is always going to be very obvious regardless of what you're using, so to try and fix it, we usually blur it afterwards, which the pattern of interleaved gradient noise also happens to excel at. Unlike white noise, which is sort of like the grenadine stain on your stainless steel table, no matter how much you blur white noise, you will still see it. If anything, it actually looks worse. IGN, on the other hand, with just a simple 1 pixel blur, looks like a beautiful angel that has descended from the heavens to make all your stochastic algorithms run faster and also look better, which when combined with temporal anti-aliasing, essentially results in a very accurate approximation of the hemisphere integral with only a few samples. That demonstration is for another day and another video though, but next time you disable TAA on the game you're playing because you don't like it, when you see the dither pattern reveal itself in the shadows, you can point at it and say, wow, thank you interleaved gradient noise for making my game run faster and look better. Anyways, that was a very long-winded way of saying that we should replace our Bayer dither with interleaved gradient noise, but will it be enough to solve Silksong's issues? Swapping in our new noise, you can see that all it takes is a very small amount to obliterate the color banding off of the screen, a one line of code solution to ward off great evil. Given this feat, I would probably put interleaved gradient noise at high universe level or maybe even low multiverse level in terms of power scaling. It passes the dark background test, but the one glow wasn't the only problem in Silksong. It is all of these intersecting glows that cause even worse banding artifacts. No need to fear, glows of many different kinds can blend together with ease now due to the immense power of interleaved gradient noise. Now, I know what you're asking. Why is our dither so effective here, yet the debanding effect Team Cherry patched into the game post-launch does pretty much nothing? Bayer dithering shouldn't be this washed, but maybe it's the problem. To check, we can return to our old friend Reshade, a generic post-processing injector for games, which will let me execute any shaders I've made on top of Silksong. The debanding effect added to the game is a post-processing Bayer dither, so we can compare by implementing our own post-processing dither that uses interleaved gradient noise instead. This works the same as earlier, but we are going to be adding the noise to the color rather than the alpha, as we are now working with the final image render and not the mesh when it's being drawn. In our Godot scene, all we needed was a very small amount of noise to fix the problem, but unfortunately, no amount of dithering is going to be able to save this mess before consuming the entire screen in noise, and that's because we missed our opportunity to fix the banding. Post-processing isn't enough here. It's too late. The grenadine has been spilled onto the stainless steel. It's over. The only solution is 6 hours soaked in OxyClean, or a much more sophisticated debanding effect, such as the one provided with the base Reshade installation. The Reshade deband effect works pretty great, and shows us a better world where Silksong colors are happy and healthy, but it runs at around 0.4 milliseconds on my 4090 at 1440p, which sounds fast, but in real-time rendering land, we would describe that as really bad. We generally expect the most expensive screen space effects to cost around 2 milliseconds on average hardware. Very powerful effects like SSAO that are worth that investment. Considering it's 0.4 milliseconds on my 4090, it's probably more like 1 to 2 milliseconds on lower end hardware. And spending an eighth of your rendering budget on an unreliable debanding effect certainly is not worth it. Instead, to fix the color banding, all Team Cherry needs to do is add this one line of code to their transparent geometry shader, trading a couple extra nanoseconds per frame to remove almost all of the blemishes on the game's visuals. It's possible this might mess with the bloom, but it's probably fine. Hopefully something I told you about today was interesting, but I'd love to hear your favorite parts of Silksong's visuals, or maybe just your favorite part. I really enjoyed Silksong very much, to the point that I'm not sure I will ever enjoy another video game again. To cope with post-Silksong depression, don't forget to check out War Thunder through the links in the description entirely for free, and claim your new and returning player rewards on PC, PlayStation, Xbox, or mobile for some fun dogfighting, tank shooting, and water shader admiring action. Or maybe you'd like one of my other videos on fun and exciting ways to generate pleasant pictures. As always, a huge thank you to all my current patrons. Without your support, I wouldn't be able to miss my flight to TwitchCon and spend the weekend writing this script instead.